In this problem, we are going to calculate, determine free energy change for the reaction given using the free energies available for us from a table in a textbook for hydrolysis of phosphorylated compounds. So we know that free energy is a state function, so it means that its value does not depend on the root, right? It just depends on the initial state and the final state of the transformation. And this allows us to be able to determine, actually make the value for the free energy change for any reaction based on the values for free energy changes for simpler reactions from which you can combine this reaction. And so, which reaction are simple reactions for which those values are given? For example, one of them is the hydrolysis of ATP into AMP, but we know that the second product will not be two phosphate groups because that's a simple reaction, right? So just one bond needs to be cleaved at a time. And so when we cleave the bond between beta and alpha phosphates of ATP, the second product will be pyrophosphate. And we know that for this reaction, the first one, free energy change will be minus 45.6 kilojoule per mole under standard biochemical conditions. So the second reaction will be the reaction that involves pyrophosphate and the remaining products of the original reaction, such as two phosphate groups. So we have a reaction of hydrolysis of pyrophosphate. So in pyrophosphate, I'll draw the structure really quick so that you understood what we are talking about. That's our pyrophosphate. So we are cleaving this bond, right? One of those bonds. And so as a result, we will get two inorganic phosphate molecules. And for this reaction, delta G is minus 19.2 kilojoules per mole, right? So in order to determine the original delta G for the original reaction, we need to actually combine those two reactions, right? And the same we will do with the corresponding values for their free energy changes. So ATP is our reactant, right? It means that we use this reaction as is, right? ATP is a reactant, AMP is one of the products. So we will use the value for the first reaction as is. And then the second reaction is also used as is because the reactant is actually the same as the second product of the first reaction. And when you add those two reactions to each other, the inorganic phosphate here will be canceling out by the inorganic phosphate as the reactant of the second one. And as a result, the only thing that is left will be those two phosphate molecules, which actually indeed the products of the original reaction. So we are adding the value for the second reaction that we wrote down as is, right, without changing the sign. And so we can calculate it to be minus 65.88 kilojoules per mole. And sometimes the second question to the question that asks you to calculate delta G will be to determine if this reaction is spontaneous under standard conditions and justify. So here, how we can determine? We can determine it by the sign of delta G, right? So we know if delta G is negative, the reaction is spontaneous in the direction how it is written, spontaneous, exergonic, or thermodynamically favored. And this is our justification. So we can say that this reaction is thermodynamically favored under standard conditions because the standard free energy change for this reaction is negative.